I'm Joel. This is Justin. We, as he mentioned, are with Open Tapestry. Prior to our work on Open Tapestry, which is an online learning platform that lets you draw from open content around the world and organize it, structure, adapt it, and measure it. We worked on a number of other projects. Did graduate work with David Wiley, did OER Recommender, OCW Finder. We're also now working with MIT on open assessments. We had earlier another session on that. So we like to build stuff. And that's kind of what this talk is about. So we're talking about STEM challenges and about how we could use open content to facilitate those. So our goal is to have more people like this. You've probably heard about this 15-year-old who came up with a test for detecting early detection of pancreatic cancer. And fewer people like this. Right? So how do you do that? How do we support STEM learning? And kind of the model, the way that I like to think about it, or a framework, is to get interest, to invite or challenge them, define the challenge, scaffold the solution of the challenge, then provide a way for learners to share the work they've done as they work on a challenge, and then to discuss and interact with others about that. And then extensions. Okay, where can I go from here? But I think the goal in my mind is always connecting learners to interesting, engaging things and giving them a pathway to engage in that content and doing things. So this is an example of a STEM challenge where, and this is really a boiled down one, but a student is asked to calculate, help her dad figure out how to bill people for digging this swimming pool and excavation. So it's not, I mean, it's a fairly well-defined problem, but not so well-defined, and there's not a strict pathway. So I've worked a lot in math education, worked with a project called the National Library of Virtual Manipulatives, and we're always kind of wrestling like, how much do you scaffold these? And then also working with math educators, it always strikes me that we talk about math as solving problems, and then we show them exactly what to do and say, repeat after me. In my mind, what is a problem? Well, a problem is something I don't know how to do, right? And so problem solving is, this is something I've not done before, and so it involves understanding a scenario, creating a formulation of how I'm going to attack this, trying something, evaluating how well I've done, backing up, trying something new, and then finally coming to something that I'm okay with, and then interpreting that in terms of some real-world action. So problem solving is a larger complex. You're all familiar with different robotics challenges where they have competitions where you build a robot to launch this frisbee or to compete. Maybe a challenge is design a room that meets these constraints. You've got this much space, you need the sink, you need these things, and so can you do this? And so one of the characteristics I think of a good STEM challenge is that there's not a well-defined solution. There's a range of solutions, and there's some criteria for evaluating those solutions. Or build a bridge, for example. This is the West Point Bridge building design contest. Build a bridge that the truck at this way can pass over, but minimize the costs. And so you've got some artifact you're designing or creating oftentimes, but then you've got some constraints. Well, what are the constraints? You've got these kind of materials. You have to try and minimize your costs. So these are just a few examples, but I would claim that they're everywhere, right? There's STEM challenges all around us, but can we harness them? Can educators find ones that are relevant to what they're trying to teach? Can they adapt them for their specific context? Can they instantiate them with a group, whether that's an intact classroom, an after-school group, or some friends, or whatever it is? So yeah, that's cool, you guys did that, right? But can I actually do that with my students? And then can we ensure that they're actually supporting learning and sort of, instead of just playing around or following some rote instructions? One thing that inspired me a lot along these lines, if you're an Open Ed faithful, is DS 106, where this is a media design program. I'm not sure. I can't remember exactly the name of the program. Digital storytelling course. And essentially what they've done is open up the assignments to the students. So you come up with a challenge and show us an example of how to do that, and then other students get to do that. So here's an example where you take a trailer for a video and remix audio from a different movie together so that they kind of make sense, but they don't really. And so there's a whole database of assignment banks where people have done this, and they do it on their own, post it on their own blog, feed it into here, then others can see it and others can try it out. And it's really cool to see the kind of interactions that happen there. So that's kind of some of what I'm envisioning for STEM challenges. It also has some of the characteristics that I think are attractive in that what I would hope that as learners are working on these challenges, that they're building a set of artifacts that represent the things they've done and the things they've learned. And they own them. They're not locked away somewhere, but they own them. So they're on their blog, they're in their systems. They have a way to share those, to refer back to those, to share them and build upon them later. So we're up in Cache Valley, about an hour and a half north of here, and we were like, let's do this with some kids. So we've got some space down in our basement of where we work. We got the kids and we painted it, got it set up, and we're doing a maker club with them, and this is kind of the basis of the type of interactions we're doing with them are these STEM challenges. And so the things that we are, again, attention and interest, and obviously different people have different types of interests, but programming, robotics, do-it-yourself, electronics, 3D printing. So how do you get a student's interest? Well, again, that varies, but I think certainly current events. The system is down at the moment. This is a current event with the Obamacare website, right? So, your brain should start flowing, well, how could we turn this into a challenge, right? And I don't have a good idea, but it seems to me that we can harness the things that are happening around us that are relevant right now and turn these into challenges. And so maybe the challenge is, how can you design a system, a scale, it could be a basis for designing for scalability, and then, okay, can we simulate that, and so on. So of course, gadgets, pop culture, anything that I think could potentially be interesting to the audience that you're working with. So what's the structure of a challenge? Well, oftentimes it's a design, right? So we're creating something, we're designing it, we're improving it, we're debugging it, we're remixing it, evaluating it. And typically we're creating some artifact, and whether it's a digital artifact or maybe it's something we're building physically, and then again we can take pictures or video of that and share that, and then we find some criteria. So here's a video game challenge where students were invited to create video games and nationally share this. And so there's, you define that. How do you capture that in a way that you can use and that you can share? So then we scaffold. So how do we actually make these things support learning? So we provide them tools that they can use, the resources for doing it, pointers to information where they can learn about it. We can organize into team structures. So with our kids, we have teams of 2, and one of them acts as a customer for the other team and a project manager, and so different structures that way. Of course, mentoring, giving them example solutions, and problem sequencing. So partial problem, worked examples, different things like this. And of course, I think an important aspect of these types of experiences is taking time to reflect on what have we done, what can we learn from that. And so having those prompts for discussion is valuable. This screenshot shows a really interesting site called TryRuby. It's tryruby.org. Ruby, my favorite programming language. You can go there, and as soon as you go there, it reads like a storybook. It's a cartoon illustrated storybook with lots of chunky bacon, and you have an interpreter right here. So it tells you what to do, and you just do it. So you're getting that feedback, you're interacting with it, and it's having a dialogue, which is scaffolding through this situation of learning how to program. So then you need to provide a way to share. So here's Scratch. This is one of the tools we're using with our youth, and it has this idea of a studio. And so everyone's working on these programs, but then they share them into the studio. Anyone can go look at what each other is doing. And so part of it is a motivation. Hey, I get to share this. And I'm not just turning this into my teacher, right? I'm putting it up here. All the other participants can see what's going on. And not only can they see it, they can hop inside it, they can look at the code, and they can actually remix it and change it and build on that. For programmers in here, there's so different tools. What supports sharing? So this is screenshot of github.com, which is a social version control. Well, it supports software development widely, but people put their code up here and people can go find stuff there, and then you can look at, like, here's all the different people participating in this project, and it makes it really easy for them to add this little piece and then we get brought into a larger project. So it's interesting to think about how can we do larger projects and support collaboration and extension via these types of mechanisms. Here's another one of my favorite tools, GeoGebra. So it's an interactive math tool that lets you combine spreadsheets, functions, computer algebra, graphs, 3D, but again, it has a GeoGebra tube, so a place where people can share the cool stuff they're doing, whether they're teachers, whether they're students, they can bring them up here, you can draw from it, the code's right there, you can take it and adapt it and extend it. So how do we support discussion? So when people share something, and this is still an interesting open question for me, but this is just Google+, right? So we've started trying to use Google+, and it's kind of working for us, not great. So I'm still in search of good ways to create small ad hoc communities around a given challenge where we can be interacting and sharing what we're doing or sharing the things that we're finding, sharing the resources that we're tapping into to be able to work on that challenge together. Extensions. This is a picture of Khan Academy's learning maps. And basically, this is a really cool thing if you've never seen this and even dig into it. You go there, and what they've done is they've mapped out all the different objectives that you might be covered in this math curriculum. But then they put them actually on an actual Google map. So you can put a background and you can drop points and stuff on there. And then you can treat this like a real map where you can zoom in. So you think of this as the cities, but then you can go see, roads and all this. So as you zoom in, you start seeing the smaller level objectives. So it's got this layering perspective of objectives. So how does this, this can help support navigation amongst challenges, but also, I think, in creating your own representation of what have I done, what have I learned. And so there's different interesting related approaches to that. I put this up here because this is a picture of a Scratch program, but remix, right? And you're starting to see this more and more on a lot of these kind of sites where remix. So I want to take this and I want to make it my own and extend it. I think that's extremely powerful and important. Artifacts. So as you're working on these challenges, there should be some residue of that, right? So you've got all these papers you've written in school, and if you're going to become an English major, it seems like you want to put them someplace on a blog or whatever, share these things. This is a screen capture of Open Tapestry, which lets you easily thumbnail clip and organize stuff that you've done. And so, we're thinking about, okay, how do you use tools like this to create basically a representation of this profile of the things that you've done and allow people to find you, to interact with you, and just talk about those kind of things. Open badges, of course, maybe there's some interaction here with being able to represent, these are the things I've done, these are the challenges I've done. What about open? I really haven't talked a lot about open yet. This is a screen capture in Open Tapestry. As you're grabbing stuff from around the internet, whether they're your stuff or whether they're shared from wherever, it detects the licenses that have been drawn from. You can also go ahead and put in your own, licenses and put as much metadata on them as you want. But what does Open do? Well, it lets you have a vast repository of things that you can quickly draw from, use to synthesize these challenges. And then, of course, if you're licensing your work open, then it facilitates this remix. So there's, again, Open is the facilitator for all kinds of things. So again, we're just thinking about what kind of platform could there be that lets you draw challenges, essentially catalog these challenges. Because like I say, they're everywhere, right? But can we draw from them and bundle them up in a way that says, okay, I can do this with this small group, and someone else could take it and adapt it and do it, and instantiate these challenges, and then support this for these groups. So I'm going to turn some time to Justin so he can play.
All right. So before I was in education, I actually did my undergrad in electrical engineering, and that's done me absolutely no good for the past 10 years. And all of a sudden, there's all these really cool things that we can do that are part of the physical world. When I started as an electrical engineer, everything we did was really, really expensive. All of the equipment that you had to have what cost hundreds of thousands of dollars, and the software cost tens of thousands of dollars. So I kind of left it behind. But now, because people are willing to be open with hardware designs, we actually have cheaper hardware that you can use in these STEM challenges. So today, I don't know if anybody's seen these. Who's seen one of these? So Makey. Everybody's seen it? Brandon has a couple of guys. So this is a piece of open source hardware. The design is open, but you can go buy them for what, $20 or something. It's easier just to buy them rather than to try to build a board and solder all this. But what this does is it provides you with an interface to the computer and
USB. You can just
yeah,
plug a
USB.
USB.
So let's find, here is one of the Scratch programs that one of the students in our Maker Lab put together. So it's pretty simple, but you can actually control it. I have to ground this stuff out here. You can control it via the Let's
See what kind of rhythm.
Yeah, let's see what kind of rhythm. Let's see if it works.
Put the focus on the screen.
Hopefully this still works in our plate of it.
It can work at the top of this one.
This is more impressive than
Oh, you have the So you take these cables,
Oh.
plug it in your plate.
Electrical engineering.
But it's still not figured out. Live demo. Okay, there we go. Joel had to come touch the computer. Now it works. So basically you can use the Makey, and then you can, and what this lets you do then is provide input. So that's not terribly significant, except that if you have a room full of kids, like I have a house full of kids, they're more interested in interacting with these technologies if you can bring it to this level. So before you get to the 15-year-old who discovers a new and more effective cure or detection for pancreatic cancer, you have to get kids to the point where, hey, I can make this computer do something besides play Minecraft, right? So if you have kids, they probably play Minecraft, I guess they can do this stuff. But so the beauty of this is you can go buy one of these. The guys at MIT licensed it, and now you have this really cool little thing. And if you want to come play with it, you're welcome to come up. I think you just have to ground yourself out. And if you wait just a second, your palms get sweatier, and that's actually what causes the connections to work. So back to the STEM challenges here. There's our contact information if you want to ask us any questions about this. We have a couple of other devices that we wanted to show you really quickly. You've probably heard of the Raspberry Pi. That's the board in the bottom right side. It's a little cheap Linux computer. You can buy it for somewhere between $25 and $35, so you can get a bunch of these for a group of students. It runs Linux, and it's fairly powerful, and you can interface it with a breadboard. If you see these little, we were going to bring one and we forgot, sorry. But these little pins right here, you have a diagram that gives you the pin out, and then you put that into a breadboard, and now you can interact with other chips and diodes, and all of a sudden your kids can build electronic things, and they can do it without ever having to touch a soldering iron, which can be a fairly daunting experience. Right here we have an Arduino. I don't know if you've seen Arduinos. They come with a little microchip. It's a microcontroller, so they are not super powerful. We're talking like 10 megahertz. So if you remember way back when you were young, the Atari and Commodore. I mean, that's about how powerful those things are. But that's okay because they typically are only meant to do one thing. So if you are really into Halloween decorations or Christmas decorations, you can plug in one of these suckers and it can control your lights, or it can scare the kids when they walk by. It's all kinds of fun things you can do with Arduino.
So just a quick question, because we kind of went on. Going back to the skill of using a soldering iron, okay? I mean, that's actually practical real-world skill that we have a use for, certainly outside North America.
Right.
Where does that fit in? As we go along, we're building, we're teaching, we're pulling all these things, we're getting fascinated, we're getting our palms sweaty. Where do we get back to that soldering skill, which is a hard skill to teach?
It is a hard skill to teach. So I think you have to be, one, you have to be motivated to do it, and two, you have to be old enough to not burn yourself on it, right? The soldering iron can do some damage. So I think at the point when you determine, not necessarily like how old do you think your kids have to be to mow the lawn, right? Like when they can operate a spinning blade and not cut their toes off, then that's a point at which you can probably begin to trust them with a soldering iron. So the second piece then is when are they motivated enough to learn how to use the system, right? So I think that that comes after you get their Raspberry Pi, you plug it in, and they played around with the breadboard, and it's flashed and done all kinds of things. Now, hey, Dad, or hey, whoever your mentor is, we want to build this really cool Halloween decoration. We need to use pneumatics. And, okay, in a second, soldering.
But I think your question speaks to this, sometimes set up as like, should we be completely didactic or should we be more exploratory in our education? And I would argue that when there's motivation to learn something, there's a lot more power behind that to be able to learn it. And at that point, you get in and say, okay, we're going to spend however long it takes to learn how to solder. But you do it in the context of something more meaningful, as opposed to saying, okay, we're going to learn to solder today. And now after we've learned all these skills, we're going to do something meaningful.
Because along with learning how to solder comes now I have to learn how to read data sheets, right? Because each one of these chips, this has a data sheet associated with it, as does this, and it shows you what these different pinouts do. So I got to learn how to read a data sheet. Then I got to learn some basic electrical engineering principles. And you learn Ohm's law, and what does that mean? And why do I put a capacitor here? And what is a capacitor versus an inductor, right? So all of a sudden, they're learning kind of beginning electrical engineering student things, and that takes some motivation, some desire, because some of that gets a little boring. But you can overcome boring if there's interest, right? So build the interest, overcome the boring. Just a couple of other little things right here. I don't know if you've seen the tile. It shows up on Facebook ads all the time. It's just a little device that you can attach to anything and it will locate your stuff, right? That was made possible, and you're going to start seeing more of these devices because of this thing right here. This is a TI sensor pod. You can buy one of these for $25. And it comes with a whole bunch of open source code that you can use to write iOS or Android applications. So these have a Bluetooth chip in them that will talk to your phone. So if you want to know what the temperature is outside, you can write a really simple app. Throw the sensor pod outside and see what the temperature is on your phone. Or if you want to, it has a motion detector, and it has a gyroscope, and it has 6 different sensors in it. I can't remember all of them right offhand. So you can take one of those, hand that to them, and then let them use some of the open source code and just tweak it a little bit, download it to their iPod or their iPhone, and wow, they get really excited, right? Because they all have iPods and iPhones, right? Or they have access to them. So that can help to build interest. Now, getting back to this is made possible because TI is releasing super low power Bluetooth chipsets. They operate on a CR2032 battery. They're the little tiny button cell batteries. They'll run for a year off of one of those batteries. That is amazing. It still blows my mind. Being electrical engineer, I'm like, these guys are crazy. But you can, getting back to your original question, when do you teach them to solder? So once you go through this process of dealing with these things, the next step is to do something more like this. That's when you bring up a Kickstarter project and your students all of a sudden use one of these Bluetooth chipsets and then combine it with a sensor, and now they have a little chip you can stick to the bottom of the roof of your house, and it detects motion, or it detects the temperature. Or there's another really cool chipset coming out. It's still in development from a Japanese company. I can't remember the name of, but it detects air quality. So right now, there's a thing called the egg. It costs about $200. It detects air quality. We live up in Cache Valley. And Utah has this problem in general with inversions. You get terrible air quality in the winter. Right now, the sensors required, or they use little lasers to count particles in the air. So it's very expensive technology because the sensors are expensive to build. Japanese company came out with this little chip, and it has all of the different air quality sensors built onto one chip, and I think it'll cost about $10. So imagine now, if you've done all of these challenges with your students, the next challenge is how do we solve the air quality problem in Cache Valley, or how do we solve the air quality problem in name your city, right? Like everybody has this problem. So that can be your challenge, and then you give them these tools. You say, okay, take this chip. What can you do? That's STEM challenges and our vision of the future. Have probably about 30 seconds. Any questions? Okay. If you want to come play with it, let us know. We've got it. We're here.
Yeah, I mean, we're definitely interested in talking to people that are doing these kind of things.
And actually,
sharing your ideas
so
and
I did
collaboration.
one.
Thank you.